Next speaker is Khalil from the German University in Cairo, and he'll present a work in collaboration with the Max Planck Institute in Stuttgart. And the title of the work is Mechanical Rubbing of Blood Clots Using Helical Robots Under Ultrasound Guidance.
Hi, I'm Khalil. I'm going to talk to you today about the work that I have done with my colleagues at the German University in Cairo and Max Planck Institute for Intelligent Systems on clearing blood clots using helical robots under ultrasound guidance. There exists a wide variety of micro-robotic systems that can be classified based on their locomotion mechanisms. These micro-robots can be pulled with the magnetic field gradients towards waypoints along the trajectory, and they can be pulled with a magnetic field gradient. Other micro-robots, like robots with sperm-like robot and helical robots, benefit from their natural design, and they can swim with lower magnetic field as opposed to magnetic micro-robots. These robots have diverse biomedical applications in nanotechnology and biomedicine. And in particular, helical robots have shown excellent performance in bodily fluids and viscoelastic environments. And these micro-robots have been transferred into in vivo experiments recently in Brad Nelson's lab. The work of Servan et al. Have shown that a cluster of micro-robotic system, helical micro-robots, can be controlled in the cavity of a mouse in vivo using imaging modality, but the control has been done using an electromagnetic system with closed configuration. Tabak et al. Recently also have demonstrated closed-loop control and simultaneous localization of a helical capsule using an electromagnetic single rotating dipole field attached to a robotic arm. In this work, we will use a helical robot with a length of 4 millimeter and diameter of 0.3 millimeter to clear blood clots in vitro. Our system aims to decrease or minimize the invasiveness of the current minimally invasive interventions to remove blood clots. It also aims to mitigate the side effects associated with the currently existing chemical lysis to remove blood clots. And we do that by using and combining an imaging modality, which is ultrasound, with the magnetic actuation using two dipole fields. We use two dipole fields, two synchronized dipole fields, in order to exert higher magnetic torque on the dipole moment of the helical robot. So the helical robot is mounted between the dipole fields, and we exert the magnetic torque. We increase the magnetic torque by having two dipole fields. We benefit from the open configuration of the electromagnetic system, and we also mitigate the magnetic forces along the lateral direction of the micro-robot. And by integrating these rotating dipole fields to a robotic configuration, we can achieve control in two-dimensional space or three-dimensional space. So the robot can be lifted up and overcome its own weight, and we can achieve control in three-dimensional space. The case we focus on is control of helical robots along one axis inside a catheter segment that resembles a blood vessel. And this blood vessel includes a blood clot. So the blood clot in our model is made of fiber, and this fibrin network entraps blood cells and platelets. So what we have is we have a helical micro-robot swimming against the flowing streams of a medium or blood, and it's interacting with the blood clot to decrease its size. And while it's interacting with the blood clot, it's also decreasing the size of the blood clot by tearing its fibrin network. So our robot is subjected to magnetic forces and magnetic torques. Also, it's subjected to gravitational forces and torques, and because it's moving against the flowing streams of blood, it's also subjected to drag forces and drag torques. Once our robot comes into contact with the blood clot, its distal tip is subjected to fretting force and fretting torque, and also when the robot bounces, it might also touch the lumen. Therefore, we have four main components, four forces and torques that contribute to our model. And because we have dynamics in low Reynolds number, we don't have to include the inertial terms. That's why the sum of the magnetic, gravitational, contact, fretting, and gravitational forces are set to 0. And this is solved by our resistor force theory-based model. Our model also predicts the removal rate of the blood clot with time by assuming that the network of the magnetic torque and the drag torque is equal to the work done or the work required to remove an infinitesimal amount of the blood clot. And this requires prior knowledge of the ultimate shear strength of the blood clot in order to be able to theoretically predict the removal rate. And therefore, we characterize the morphological properties and rheological properties of the blood clot in order to enter this model, this parameter to our RFT-based model. So we characterize the blood clots, fresh blood clots, 1 hour old, using scanning electron microscopy images, and we realize that the clots are made of compressed cells within the fibrin network of the clot. The second thing is the detection of the shear modulus and the ultimate shear strength. So we characterize the ultimate shear strength for at 2 temperatures, at body temperature and at room temperature, and it turns out that the ultimate shear strength is around 1 kilopascal. This ultimate shear strength is used in our RFT-based model in order to predict the behavior of the clot, of the robot and the clot also. So as we see in the simulation results, our robot swims towards the clot, and once it interacts with the blood clot, it stops moving along its long axis, but keeps rotating and tearing the fibrin network of the blood clot. And after some time, we observe a helical trajectory inside the blood clot. Our model also predicts the removal rate of the blood clot against frequency, which I will describe with experimental results. Our experimental results are done on an in vitro model. That in vitro model contains a catheter segment. In this catheter, we induce flow rate of 10 milliliter per hour. It's as if we have a flowing stream of blood. Inside the catheter segment, we have a blood clot and the robot swimming against the flowing stream of the fluid. This catheter segment is contained inside a gelatin block to achieve air-free coupling with the ultrasound transducer. And this transducer provides ultrasound scan to the control system. The whole system is contained between 2 rotating dipole fields to actuate the helical robot at a distance without contact. Also, we have 2 cameras to provide feedback and to detect the size of the blood clot with time. So we have to localize the micro robot using ultrasound feedback in order to feedback this position to the control system. So we started by looking at superficial blood vessels. Superficial blood vessels that are very close to the ultrasound probe. And we found that we can, with the ultrasound feedback, we can detect micro-robots with diameter of tens of microns. But this is because the robot is very close to the transducers, then we can use high-frequency ultrasound wave. We also detected the resolution of the system when we increase the depth, because we also want to know if we can use this technique for deeper tissue, for vessels at deeper distances. But of course, there is a trade-off between accuracy or solution and also the size of the robot. Because if we get deeper, we will have to use higher energy ultrasound waves with lower frequency, and then the resolution of the system will be decreased. After localization, we feedback this position to the control system, and we subtract the position of the robot that's detected by the ultrasound from the desired position of the clot, and we generate a simple proportional control. Because our system is characterized with low Reynolds number, so there is no need to add a derivative term. Our system is already overdamped. And the second control law is just synchronizing the 2 dipole fields together to increase the magnetic torque and to mitigate the lateral forces along the lateral direction of the robot. We have performed 30 closed-loop control results using 30 different helical robots, and our average steady state error is around 0.8 millimeter, and the closed loop control under ultrasound guidance is done at an average speed of 5.3 millimeter per second. And after the closed loop control, we start interacting with the blood clot. Once the robot arrives at the site, at the blood clot site, we start interacting with the blood clot. We start tearing its fibrin network. We find a relation between the rubbing frequency of the robot and the removal rate. So below 20 hertz, the rubbing or the helical robot was not efficient because the robot was not able to swim because it has to overcome the flowing streams of the fluid. Above 45 hertz also, the rubbing was not efficient because of the increased damping on the robot. And we found an optimal rubbing frequency of around 35 hertz in between, and this also matches what our RFT-based model prediction. It's highly likely that this approach will be used in a combination with chemical lysis. And in chemical lysis, anticoagulant agents will be used, and therefore it has to be used at the body temperature, not at room temperature. Therefore, all our experimental work is done at body temperature, at 37 degrees. So we observed that at room temperature, the removal rate of the blood clot is around 0.6 millimeter cube per minute. And when we go to body temperature, it's around 0.5 millimeter cube per minute. Another worry we had is that this is a mechanical technique where the robot interacts with the blood clot. So we had the risk of forming small fragments that might swim along the bloodstream and might clog other smaller vessels. And that's why we collected all the mixtures in these small cuvettes. All the mixtures past the robot and the blood clots are collected and they are analyzed under microscope. First, we haven't found any fragments, any small fragments, and also the microscopic analysis showed that the blood cells they break free from the fibrin network because of the action of the robot as opposed to the idle case. So finally, we have achieved closed loop motion control of helical robot towards blood clot using ultrasound feedback. We have characterized the properties of the blood clots and used this in our theoretical model. And we have validated the efficiency of our model at 2 different temperatures. As part of our future work, we are translating our experiments into in vivo experiment. We have managed to insert our helical robot inside the jugular vein of a rabbit, and we are now working on controlling the robot in closed loop inside the jugular vein of the rabbit. And finally, I would like to thank you for your time.
Thank you for the presentation. Do we have questions? Yeah.
Very impressive system. Looks quite promising clinically. I wonder about interaction of the robot with the vascular wall. Is it going to rip the endothelial cells off the vascular lining, or are there going to be issues around that lack of precise control at the tip?
Our robot, because we are depending on magnets, so indeed, if we use only a single single rotating dipole field, we will have a pulling force. We will have a pulling force along this direction. But as you see, because we are using 2 dipole fields, then the magnetic force along the long axis, along the lateral axis of the robot is decreased. So if you only use 1 rotating dipole field, you will be able to do the same job, but in the expense of hitting the lumen. And this might cause tissue damage because you have 1 magnet, and then the robot will be pulled while it's rotating. And that's why we add the configuration of 2 or more rotating dipole fields in order to decrease the magnetic force along the lateral direction of the robot. This also is an interesting approach. Why? Because I also benefit from the gradient along the long axis. because I don't want also to lose the magnetic force because it's helping propulsion.
Hello. Hi, very interesting work. My question actually will be something which is similar to the first question. Did you consider the biofluid dynamics of the medium in which the robot is swimming, and also the interaction, like I said, the wall interaction? So did you model the friction that can happen? Of course, you have taken care of it, as you said, but these two things, biofluid dynamics of the medium and the friction of the swimmer in the medium.
Our resistive force theory model takes care of that. So we have 5 main forces that contribute to the dynamics. The first force is a driving force and torque. These are the magnetic. Then we have gravitational, and then we have drag forces. Drag forces are also responsible for propulsion. And in the drag force, all the rheological properties of the fluid will be there in the drag coefficients. So for instance, here you have matrices, and these matrices, they contain the resistive coefficient, and the resistive coefficient, they depend on the geometry of the robot and the properties of the fluid. So if I do experiment in saline, the model will predict different results from another guy who will do the experiment in whole blood or serum. So all this will be taken care of because the viscosity will change and other rheological properties of the fluid. So you can do this by just changing or entering the correct values in the equation of the drag equation for the torque and the force.
Okay, for the sake of time, the last question, and then we'll move forward.
Yeah, so in terms of the robot itself going through the clot, so in a typical atherectomy device, you sort of have a sieve at the other end, right, which catches all the particles that are generated as a result of that. So in your case, when you have this helical robot going through the clot, you will generate particles, and I know you talked about it very briefly, but that's a big concern, right? I mean, how do you take care of any particulates that are generated?
Yes, yeah, true.
Because that can cause problems downstream.
Well, yes. We were really concerned about small fragments that might clog other arteries, smaller vessels. So we think that our approach won't be used alone. It has to be used in combination with chemical lysis. So we shouldn't use just mechanical rubbing 100%. We should use it in a combination with chemical lysis to make sure that if we had small fragments, that they will dissolve by the anticoagulant agent. This is one of the methods that we can use to overcome this problem.
Okay, so let's thank the speaker again.